Okay, so here we have where antiderivatives get a little bit tricky. So I have told you before when we were talking about antiderivatives that there's no way to undo the product rule, not in Calc 1 anyways, and there's no way to do the quotient rule, not ever. There is a way to undo the chain rule. So we have these antiderivatives, or these derivatives I guess, that look like they're in perfect form for the result of a chain rule. And so that's what we're going to be working with today, is figuring out how to undo the chain rule, which when you take the derivative of something using the chain rule, the derivative gets much more complicated than the actual function. So when you take the antiderivative of the result of a chain rule, the antiderivative will actually get much, much simpler. And you'll see exactly what I mean when we take a look at these first couple of examples. Okay, so take the derivative of this thing right here using the chain rule. We're going to start off with a very simple example. Okay, so take the derivative of this thing right here. So we say y prime equals, so we start with the derivative part. The derivative part means we take the derivative of the main function. The main function is sine, its derivative is cosine. So the derivative part is cosine. Remember, we always leave the nested function in place. Then when we're taking the antiderivative, we multiply by what we call the correction factor, which is the derivative of the inside function. So we take the derivative of the inside function. The derivative of 3x plus 1 is just a 3. Okay, so I'm going to leave it like that, just the way it is, so you can see all of these little pieces. Okay, so we've got the derivative part, and then the correction factor, which is the derivative of the nested function. And this piece right here is the nested function. Now notice that I have brackets around this whole piece, because the whole piece is the derivative part. You just happen to have a nested function in there, and the correction factor is always the derivative of the nested function. Okay, so what the antiderivative format would look like is going to be something like this. If you take the antiderivative of a function like this, so we're going to write out exactly what the chain rule thing looks like. So we've got f prime, that's the derivative part, with the nested function in place, and then times g prime of x. Okay, dx. So what I'm saying is if we take the derivative of this and we get this, we should take the antiderivative of this to get this. Okay, so that's what we're looking at here. If I asked you to take the antiderivative of the result of a chain rule, what happens is that you've got this derivative part with the nested function inside, you've got the correction factor. If you take the antiderivative of this, you end up with this. And then of course you have a plus c. So the antiderivative of f prime we know is f, but when you undo the chain rule, it's almost like the correction factor gets sucked right back inside, because that's where it came from to begin with. We multiplied by the derivative of the nested function, and so when we take the antiderivative, it's almost like it gets sucked right back in, because if you take the derivative of this thing here, you'll end up with this. Okay, so it's going to seem a little bit tricky at first. We're going to do this process called undoing the chain rule if something looks like it's in chain rule form. Okay, so this example 1, part A, we've got this thing right here, and we're going to try to just look at all the different pieces. Okay, so the derivative part is the e part, the e raised to the something. So this is the derivative. We're going to use some just abbreviations here. That's the derivative. We've got our nested function right here. The nested function is the x squared plus 4, and lo and behold, the derivative of x squared plus 4 is 2x. So right here we have our correction factor. Okay, so when we take the antiderivative, we take the antiderivative of this main function here. The antiderivative of e to the x is still e to the x. But instead of e to the x, you have the nested function in place. And then after that, you just tack on a plus c. So yes, when you take the antiderivative of something like this, it actually gets much simpler. But you could check by taking the derivative of this again. If you take the derivative of this, derivative of e is still e, so we get e to the x squared plus 4, but then because it's a chain rule, we would multiply by the derivative of x squared plus 4, and that's exactly what you get right here. Okay, let's look at the next one. Okay, so if we look at all of our different pieces, we've got this piece right here is the derivative. The x to the 5th plus 1 must be our nested function. And let's check. So the derivative of the nested function, the derivative of x to the 5th minus 1 is, in fact, 5x to the 4th. So that is our correction factor. So all we need to worry about is taking the antiderivative of this main piece that we have right here. So the function that gives us this as a derivative, the 1/2 x to the negative 1/2, is x to the 1/2. But instead of x to the 1/2, we do x to the 5th minus 1 to the 1/2. And then you tack on a plus c. So we can always do a quick double check, like this one. Let's check it. So we take the derivative of this. The 1/2 comes out front. We leave the x to the 5th minus 1 in place. We drop the power down to a negative 1/2. And because we need a chain rule, we multiply by the derivative of x to the 5th minus 1, which is 5x to the 4th. The derivative of the plus c just gives us 0. So we land right back here. So that means that this must be the answer. Okay, a couple more examples. Let's try this one. So let's identify, like, this piece right here is our derivative. That's the derivative part, I guess. The nested function is the cosine. And then what's the derivative of cosine? Negative sine. And so there's our correction factor right here. Okay, so all we need to worry about doing, so instead of like 3 times cosine squared, let's think of this as like a 3u squared. And we want to figure out what's the antiderivative of 3u squared. The antiderivative would be u cubed plus c. So that means the antiderivative would be cosine cubed plus c. And you can always do a quick check. You can always take the derivative of this again and see that you get the exact same thing. The 3 would come out front, power would drop down to 2, and then we'd multiply by cosine's derivative, and we'd land right back here. Okay, one more in this form. We've got this whole piece right here is the derivative part. Here's our nested function, the x squared plus 6. And then there is a perfect derivative of the nested function. The derivative of x squared plus 6 is 2x. So there's our correction factor. So we need to take the antiderivative of 4u cubed. The derivative of 4u cubed is x to the 4th. But instead of x to the 4th, we do x squared plus 6 to the 4th. And then you just tack on a plus c. And once again, you can always just take the derivative of this and check to see that you got the right thing. Okay, so all of those ones that we just saw were ones that perfectly fit exactly what a chain rule would look like. They're not always going to look exactly like that. So let's take a look at this one. If we try to take the antiderivative of this, you've got this same piece right here. So like, all right, so that must be our derivative, the sine part. And so the 7x minus 5 must be the nested function. And then you go to look for the correction factor, just like we had all of right here, and the correction factor is missing. We don't have the correction factor. Okay, so the problem is there is no correction factor. Uh-oh, what are we going to do? So here's the thing. This part's great. My nested function is a 7x minus 5, so I'm supposed to have a correction factor of 7. So what we do, and again, you're going to be a little freaked out by this, but I'll explain it as we're going. You just add it in. But just like we know from algebra, you can't just add something in without balancing it out. So what we would do is we would just throw the 7 right in there. I'm going to see if I have a different color. So we would just throw the 7 right in there. Because you're like, well, I need my correction factor. Okay, there it is. But you can't just multiply something by 7. That totally changes it. So what you do is on the outside, you throw in a 1/7, which we call a balancing factor. So you throw in any correction factor that you need as long as it's just a constant. And then you balance it out with what we call a balancing factor. Okay, so we're going to look at a couple of examples that do just that. So undoing the chain rule and then using a balancing factor. So let's walk through what we have. So here again, this is the derivative piece. The 3t minus 4 is our nested function, but we are missing our expected correction factor. So let's rewrite this thing. So we've got, in a row, we've got e to the 3t minus 4, same thing that we started off with. So we want to try to figure out, well, if this is our nested function, what correction factor are we expecting to see? And so since our nested function is 3t minus 4, which is linear, we're expecting to see a derivative of 3. So what we do is we just throw it in there. We're like, well, we want a 3, we're going to get a 3. However, it doesn't just work that way, that you can just throw things in. You can't just multiply anything you want by 3. But if you multiply by 3, what we can do is balance it out with a 1/3. Okay, so that's why we call that the balancing factor. So we've got our derivative, we've got our nested function, now we have our correction factor, and we're throwing in this new thing that we call the balancing factor. If we were to multiply 1/3 times 3, we'd get 1 and we'd land right back here. However, we need all of these pieces in order to undo the chain rule. Okay, so don't forget when we take the antiderivative, we've got this 1/3 out front, and then we're going to take the antiderivative here. So the antiderivative of e is e. We leave our nested function in place, and then tack on a plus c. So if we were to take the derivative of this, what would happen in the chain rule is that the 3 would come out front and multiply by the 1/3, and that's why we wouldn't have a coefficient there. So this is our antiderivative. Okay, let's do this again. So we've got, this is our main function right here. This is the derivative. We've got a nested function. Okay, and then our nested function is 1 minus theta, so what we're expecting to see would be the correction factor. So we always just kind of throw in whatever correction factor we want. Okay, so works like this. Let's separate these out first, just because theta is very simple. We can take the derivative of that, and then let's do minus. This is always a good idea, especially if one of them requires undoing the chain rule and the other one doesn't. So here's what we're going to do. We're expecting to see a -1, so we're just going to throw in a -1. But we can't just multiply things by a -1, and so we balance it out with the reciprocal, which is also a -1. Okay, so that's how that works. Now let's take some antiderivatives. Antiderivative of theta is just a 1/2 theta squared. That's just a nice, neat power rule. Now here, when we take the antiderivative, this piece right here is our derivative. This is our nested function. We just added in the correction factor. Okay, so when we take the derivative of this, the antiderivative of cosine, the function that gives us a derivative of cosine, is sine. And then we leave the 1 minus theta in place. Don't forget your plus c. So we take the derivative of this, we know we land back here. If we take the derivative of this, the derivative of sine is cosine. We leave the 1 minus theta in place, and then we multiply by a -1, and that's how we end up right here. You can always, always, always check your answers with these, and that's the beauty of antiderivatives, even with undoing the chain rule. Okay, this one. Take a look here. We've got, this is our derivative. This is our nested function. The derivative of x squared plus 6 is a 2x, so we actually do have our correction factor. What we're missing here is not the correction factor, it's actually part of the derivative. So if we have a power of 3 here, we're expecting to see a 4 right there. Okay, so we're going to rewrite this. So this time it's actually a piece of our derivative rule that we're missing, so we're just going to throw it in. So we want a 4 right here. We'll talk about balancing that out in just a second. Then times the 2x dx. So now this is complete. Now I have my whole derivative piece right here. Because if you take a derivative, you're used to seeing 4x cubed as the derivative. So since I just tossed that 4 in there, I need to balance it out with a 1/4. Okay, so now let's take the antiderivative. So I'm going to have 1/4 as part of my answer. The antiderivative of 4u cubed is u to the 4th. So that means I get x squared plus 6 to the 4th, and then plus c. So if you take the derivative of this, the 4 comes out front, times 1/4, that's why I don't have a coefficient here. Power drops down to a 3, and then I multiply by the derivative, which gives me a 2x. So we've seen these examples. We've seen examples where the correction factor is missing, and now we just saw this example where even a piece of the derivative part was missing. So these last couple we're going to look at. If we flip the page to this last one, these ones are now missing both. Okay, so we're going to walk through, throw in everything that we're missing, and then balance it out. Okay, so this one right here, you have sort of the derivative rule. If this is a power of 10, you're expecting to see an 11 right there. So let's start with that. So let's rewrite this. So we're expecting to see an 11 right here. So we're just going to write it in. Raised to the 10th. And then because of this 2x plus 9, you're also expecting to see a 2 right here. So now it's complete. It's got all the pieces that we need. Here's our full derivative part. Let me label everything. Here's our full derivative piece right here. Here's our nested function. of the 2x plus 9, and then you're expecting to see the derivative of the 2x plus 9, which is 2. But now I just threw in an 11 and a 2, which means I really threw in a 22, and so I need to balance it out with a 1 over 22 on the outside. That's what that balancing factor is there for. So if I were to redistribute everything, multiply all those constants out, I'd land right back here, but that's not the point. That would be counterproductive. So when I take the antiderivative, I have my 1 over 22 out front, and then the antiderivative of this piece that I've got bracketed right here. Power goes up to 11, I divide by 11, so I just get 2x plus 9 to the 11th plus c. Remember when you take the antiderivative, when you're undoing the chain rule, it's almost like the correction factor gets sucked back into the nested function. All right, and you can always, again, just double check. Take the derivative of this, and I promise you, you will land right back here. So one more of these. We're going to rewrite it, throwing in everything that we expect to see there. So if we have a power of 3, we're expecting to see a coefficient of 4. And then since the nested function is an x squared plus 6, we're expecting to see a 2x. We only see a 2, not a 2x. Now if the x was missing, we couldn't do this. The only reason, or the only thing we can do is play around with constants. We can't play around with variables. So if the x was missing, you can't just toss that in and balance it out. The only thing you can put out front is a constant. So I just multiplied in a 4 and a 2 that weren't there before, so I need to balance it out with 1/8. Okay, so now we've got all of our pieces. Here's our derivative piece. The x squared plus 6 is our nested function, and the 2x is the correction factor. And then, of course, we have our balancing factor out front to balance out the fact that I just threw in a 4 and a 2 where there didn't used to be one. So my answer is definitely going to have that 1/8. The antiderivative of 4u cubed is u to the 4th. And then that correction factor kind of gets sucked back in. And don't forget your plus c. Okay, let's do one more here, kind of a different example. First of all, I want to rewrite this. I want to rewrite this as cosine of x raised to the 7th power and then times sine, so you kind of see all the little pieces here. So here's what I've got. I've got almost a full derivative. I've got almost a full correction factor. Let's start to figure out what we've got here. So if this is a power of 7, I would be expecting to see a coefficient of 8 out front. That gives me my full derivative rule. And then because my nested function is cosine, the derivative of cosine is negative sine. So I would expect to see a negative sign right here. So remember, this part is kind of weird. It freaks people out. They're like, well, why can't I just change the integrand? I can't just change the integrand. You're not. We're only changing the integrand by constants. That's the only thing that's allowed. And you can change by constants because you can always balance constants out by throwing a constant out front here. So I just multiplied in an 8 and a negative 1. So I'm going to balance out that negative 8 with a negative 1/8. Oops. Okay, so there's my balancing factor. I've got all the pieces. Here's my full derivative rule. Let's throw in an r. You know, derivative rule. Use the whole thing. Here's my nested function. And then the derivative of the nested function. There's my correction factor. And then I just threw in this balancing factor. Haven't been labeling that, but there it is, the balancing factor. So when I take the antiderivative, I still have the negative 1/8 as part of my answer. The antiderivative of 8u to the 7th is u to the 8th. So cosine to the 8th. My plus c. Okay, all done with the antiderivatives.